Hello and welcome back. In today's video, we're overclocking the Intel UHD Graphics 770 integrated in the Raptor Lake desktop CPUs all the way up to 2.5 GHz using the Asus ROG Maximus Z790 Hero motherboard and EK Quantum custom loop water cooling. In my very first Raptor Lake overclocking video, I hinted that I would maybe return to also overclocking the integrated graphics. However, I didn't really plan on following through with that suggestion because the IP and the overclocking process is identical to Alder Lake. But when I quickly tested the overclocking capabilities of the Raptor Lake IGP, I figured this is interesting, let's do this anyway. So this will probably be another quick guide, but let's jump in. The Intel UHD Graphics 770 is integrated in Intel's Core i9-13900K processor and features the XELP GPU microarchitecture that was first introduced on 11th generation Raptor Lake. The UHD Graphics 770 is identical to the graphics IP integrated into the Alder Lake processors. Therefore, the performance and overclocking experience will be very similar too. However, since Raptor Lake sports an upgraded Intel 7 process with 3rd generation Intel superfin transistor, we may expect higher clock frequencies like we saw with the P-cores. The UHD Graphics 770 of the 13900K has 32 execution units and a maximum boost frequency of 1650 MHz, which is 100 MHz higher than its brother integrated into the Core i9-12900K. In this guide, we will cover 3 overclocking strategies. First, we enable Asus multi-core enhancement and Intel XMP 3.0. Second, we increase the graphics frequency to 2.1 GHz using the graphics ratio. Next, we use base clock frequency overclocking to increase the graphics frequency further. But before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start any overclocking, of course, we have to check the performance at stock settings. Please note that this Asus ROG Maximus Z790 Hero motherboard unlocks the Intel Turbo Boost 2.0 power limits out of the box. So for us to check the performance at stock settings, we first have to go into the BIOS and go to the Extreme Tweaker menu, set Asus multi-core enhancement to disabled and force all limits, then save and exit the BIOS. Here's the benchmark performance at stock. When running Firmark GPU stress test, the average GPU slice clock is 1650 MHz and the average GPU unslice clock is 1400 MHz with 1.065 volt. The average memory clock is 2400 MHz. The average GPU temperature is 45 degrees Celsius and the average GPU power is 12.539 watts. Now let us try our first overclocking strategy. However, before we get going, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default. That's useful if you want to start your BIOS configuration from scratch. The Clear CMOS button is located on the rear I/O panel. In our first overclocking strategy, we leverage Asus multi-core enhancement and Intel Extreme Memory Profile 3.0 technologies to improve our system performance. Asus multi-core enhancement is a single BIOS option that allows you to unlock or unleash the Intel Turbo Boost 2.0 power limits. Essentially, it allows you to run the processor at the maximum frequency at an indefinite amount of time. Asus has enabled MCE by default on most of its Z790 motherboards. Intel Turbo Boost 2.0 technology allows the processor cores to run faster than the base operating frequency. Turbo Boost is available when the processor works below its rated power, temperature, and current specification limits. The ultimate advantage is opportunistic performance improvements in both multi-threaded and single-threaded workloads. The Turbo Boost algorithm works according to a proprietary EWMA formula. That stands for exponentially weighted moving average. There are 3 parameters to consider: PL1, PL2, and tau. Turbo Boost 2.0 technology is available on Raptor Lake as it's the primary driver of performance over base frequency. Adjusting the Turbo Boost 2.0 power limits is, strictly speaking, not considered overclocking, and that's because we don't change any of the electrical, thermal, or frequency parameters of the CPU. Intel provides the Turbo Boost 2.0 power limits as a guidance to motherboard makers and system integrators. The motherboard makers and system integrators can then use these values to make sure that their motherboard designs or their system designs can handle the base performance of the CPU. Intel Extreme Memory Profile, or XMP, is an Intel technology that allows you to automatically overclock your system memory for better system performance. It is built upon the JEDEC specification and allows memory vendors such as G.SKILL to program higher performance settings onto their memory sticks. Intel Extreme Memory Profile 3.0 is the new XMP standard for DDR5 memory. It is primarily based on the XMP 2.0 standard for DDR4, but has additional functionality. There's a lot more to the new XMP 3.0 standard, which is outside of the scope of this overclocking guide. If you're interested in more details about XMP 3.0, check out my Alder Lake launch video. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to XMP1. Set ASUS Multi-Core Enhancement to Enabled Remove All Limits. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Enabling XMP and unlocking the Turbo Boost 2.0 power limits minimally impacts our benchmark performance. We see a performance increase of up to 4.5% in Final Fantasy, but we only improve by slightly over 2% on average. When running Firmark GPU stress test, the average GPU slice clock is 1650 MHz and the average GPU unslice clock is 1400 MHz with 1.065 volt. The average memory clock is 3900 MHz. The average GPU temperature is 45 degrees Celsius and the average GPU power is 11.771 watts. In our second overclocking strategy, we finally get around overclocking the integrated graphics. And just like in SkatterBencher number 33, where we overclock the Alder Lake integrated graphics, it's really simple. You just set the maximum ratio and that's it. No further adjustments required. It's just stable. To make this OC strategy a little bit longer than just me showing you which setting to change, let's have a look at how overclocking the integrated graphics works on a technical level. The term integrated graphics already reveals that the UHD Graphics 770 XDLP is integrated into the Raptor Lake CPU die. While the integrated graphics takes up a sizable chunk of the total die, most of the chip is used to place the 8 Raptor Cove CPU P cores and 16 Gracemont CPU E cores, the cache and the ring bus. The design of the XELP integrated graphics includes 3 main parts: the slice, the unslice, and the display block. The slice is a cluster of sub-slices, each containing elements of the actual graphics compute engine, like the execution units. It is the part that powers your games and any compute tasks. The unslice holds the elements with fixed function geometry capabilities and fixed function media capabilities. It also contains the connection to the ring bus via which the IGP can send and receive data from the system memory. The display block contains support for the display outputs like HDMI or DisplayPort. When it comes to clocking, the IGP frequency is based on the base clock frequency or reference clock. By default, the BCLK is 100 MHz, but it can be increased when overclocking. For the integrated graphics, the base clock frequency is first halved, then multiplied by the graphics ratio to obtain the final operating frequency. Since Alder Lake, the slice and unslice are decoupled. That means they're running at different frequencies. The default maximum boost frequency of the slice is 1650 MHz, and the default maximum frequency of the unslice is 1400 MHz. However, like Rocket Lake and Alder Lake, we can only control the slice frequency using the graphics ratio. On Raptor Lake CPUs, the maximum graphics ratio limit is 42. That is the same as Alder Lake and Rocket Lake, but lower than the previous generation Comet Lake, where the maximum ratio limit was 60. The Raptor Lake integrated graphics supports the graphics dynamic frequency feature. Dynamic frequency essentially allows or enables the Intel CPU PCU or power control unit to assess the current, the power, and the thermals of the IGP to determine the upper limit of the IGP frequency. The dynamic frequency relies on the factory-fused voltage frequency curve of the IGP to determine which voltage and which frequency to apply. For this guide, I extracted the VF curve for my specific CPU. As you can see, even though the maximum default frequency is 1650 MHz, the voltage frequency curve scales up to 2.1 GHz. As we mentioned, the graphics frequency is partly a function of the available thermal, current, and power headroom. The Turbo Boost 2.0 technology manages that aspect of the integrated graphics. Turbo Boost 2.0 distributes the available power budget among the CPU and graphics cores depending on the workload. So if you have a heavy graphics dependent workload and no CPU load, it will decrease the CPU frequency in favor of boosting the graphics frequency higher. Of course, knowing that the power budget of the Raptor Lake integrated graphics is about 15 watt, we don't expect this Turbo Boost power budgeting to impact anything related to our system performance. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to XMP1. Set ASUS Multicore Enhancement to Enabled Remove All Limits. Set Max CPU Graphics Ratio to 42. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. Increasing the frequency of the UHD Graphics 770 from 1650 MHz to 2.1 GHz will improve the system's performance. We see an average performance improvement of almost 24% and a maximum performance increase of up to 29.13% in CSGO. The quick-sync performance, as measured by Handbrake, remains at about plus 9%. That's because the slice and unslice frequency is decoupled. So by setting the graphics ratio, we only overclock the slice. Since the media encoding functions like quick-sync are part of the unslice, the performance is not impacted by the GPU overclock. When running Firmark GPU stress test, the average GPU slice clock is 2100 MHz and the average GPU unslice clock is 1400 MHz with 1.085 volts. The average memory clock is 3900 MHz. The average GPU temperature is 48 degrees Celsius and the average GPU power is 15.975 watts. In our third overclocking strategy, we will leverage reference clock overclocking to push our graphics beyond what's possible with the graphics ratios. We used a BCLK of 125 MHz to achieve a slice frequency of 2.5 GHz and an unslice frequency of 1.75 GHz. Furthermore, we'll also make some adjustments to the voltage, for which we'll tune the VCC GT voltage rail. So let's get started with looking at the clocking and voltage topology of a Raptor Lake processor. Raptor Lake inherits the CPU internal clock generator from Tiger Lake. The standard Raptor Lake platform has a 38.4 MHz crystal as a reference clock to the PCH. The PCH then generates 3 clocks: 38.4 MHz reference clock for the CPU internal clock generator, 100 MHz PCI BCLK for the PCIe DMI and I/O, and a 24 MHz frequency for TSC display and ISVID controller. The CPU internal clock generator then generates the 100 MHz base clock frequency for all the parts inside your CPU. However, Intel also offers the option to use an external clock generator. You'll typically find this on high-end motherboards. Whichever way you get the 100 MHz BCLK, this base clock frequency is multiplied with specific ratios for each of the different parts in your CPU. The GT frequency or graphics frequency is based on the same 100 MHz BCLK, but is first divided by 2 and then multiplied by the GT ratio. As mentioned before, the slice and unslice are decoupled, meaning they run at different ratios. As you now understand, increasing the base clock frequency will impact many parts inside our CPU. So apart from adjusting the graphics ratio, we also need to change the default CPU ratios, ring ratio, and DDR5 memory ratio. Generally speaking, there are two ways to configure the CPU ratios on a Raptor Lake CPU. Sync all cores or by using the turbo ratio configuration. Sync all cores sets one ratio that is applied to all cores. It is very much the traditional way of overclocking. Turbo ratios allow us to configure the overclock for different scenarios, ranging from one active core to all active cores. That enables a much more dynamic performance profile. Since we are planning to increase the base clock frequency by 25%, we will adjust the default turbo ratio configuration to mimic the standard configuration as much as possible. For example, to achieve the maximum single core turbo boost 2.0 frequency of 5.8 GHz, we will set the ratio to 46x instead of 58x. On Raptor Lake CPUs, there are a total of 7 different voltage inputs. The one relevant for overclocking the UHD Graphics 770 is called the VCC GT. This voltage powers the GT or integrated graphics, including the slice, unslice, and display block. You can program the graphics voltage in override and adaptive voltage mode using Intel's overclocking toolkit. In override voltage mode, the voltage will remain constant, whereas when using adaptive voltage mode, the graphics voltage will dynamically change depending on the workload. You can set the adaptive voltage mode directly, which maps against the configured boost frequency, or you can use an adaptive voltage offset, which offsets the entire voltage frequency curve. Note that not all motherboard BIOSes provide full access to the entire Intel Overclocker's toolkit, so some of the options may not be available in every BIOS. On this motherboard and this BIOS, we can only configure the GT voltage or the VCC GT voltage rail by programming the voltage regulator directly, so not by programming the processor. That means that any voltage offset that we configure in the motherboard BIOS will result in an increase of effective voltage, but may not be visible in any of the monitoring software that we're using to track what's going on with the system. A crucial setting when we overclock the BCLK is BCLK aware adaptive voltage. This option has been available on Intel processors since Kaby Lake in 2016. Long story short, in adaptive voltage mode, the factory fused voltage frequency curve of a CPU core maps a voltage against a ratio. For example, 45x may map against 1.175 volt and 52x may map against 1.35 volt. When you overclock using the BCLK frequency, the voltage may not be suitable for the resulting frequency. In this specific case, we have increased the BCLK frequency to 125 MHz and have decreased the CPU ratios to match the default specification. Without enabling BCLK aware adaptive voltage, the CPU would look up the voltage for the 45x ratio, for example 1.175 volt, then use this for 5.6 GHz. That would not work out very well. By enabling this setting, the CPU takes account of the adjusted base clock frequency, and the CPU will use the appropriate voltage based on the effective frequency instead of the configured ratio. BCLK aware adaptive voltage works for all VF power domains in the CPU. The voltage frequency power domains include the CPU cores, ring, and integrated graphics. So it also has a significant impact on our IGP voltage frequency curve. If we set the BCLK frequency to 125 MHz and disable BCLK aware adaptive voltage, the voltage frequency curve would look as follows. For example, we see that for 1500 MHz, the voltage would be 0.92 volt instead of the default 1.005 volt, and thus may be unstable. When we enable BCLK aware adaptive voltage, the integrated PCU will calculate the correct voltage based on the actual frequency. So the voltage will be 1.005 volt again. There are three things in particular to pay attention to when attempting to overclock the Raptor Lake integrated graphics. The limit of the slice frequency, the limit of the unslice frequency, and knowing the actual effective voltage. Testing the limit of the slice frequency is pretty straightforward. As you increase the BCLK, the slice frequency increases accordingly. You can just use a 3D workload to test the stability of the slice frequency. To check the actual frequency, I rely upon GPU-Z sensor information. Testing the unsliced frequency is similarly straightforward. As you increase the BCLK, your unsliced frequency will rise accordingly. You can then use an application like Handbrake to check the QuickSync stability. Checking the actual GT voltage is not as straightforward as I had hoped, as it seems that none of the tools that I usually rely upon for voltage reporting is reporting the correct voltage when I overvolt using the BIOS options. While GPU-Z reports the proper VID request from the GPU to the VCC GT voltage controller, Hardware Info and XTU report an unusually low VID. When we increase the GT voltage using the voltage offset available in the BIOS, none of the tools report the accurate voltage. And that's because we program that voltage offset directly on the voltage regulator and not using Intel's Overclocker's toolkit. We can easily demonstrate this using Intel's Extreme Tuning utility, which gives access to configuring the processor directly. If we set a plus 200 mV offset using XTU, it also increases the reported voltage in GPU-Z. However, GPU-Z reports the default voltage if we set the same plus 200 mV offset using the BIOS options. So to know what voltage we're running at, we have to manually increase the reported voltage in GPU-Z by the configured amount in the BIOS. In this OC strategy, we pair the 125 MHz BCLK with a slice ratio of 40x and an offset of 0.315 volt. That results in a slice frequency of 2.5 GHz, an unsliced frequency of 1.75 GHz at 1.4 volt. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to XMP1. Set a BCLK frequency to 125. Set ASUS Multicore Enhancement to Enabled, remove all limits. Set DRAM frequency to DDR5 7750. Set Performance Core Ratio to by-core usage. Set 1-core and 2-core ratio limit to 46. Set 3-core to 8-core ratio limit to 44. Enter the specific Performance Core submenu. Set Performance Core 0, Core 1, Core 4, Core 5, Core 6, and Core 7 specific ratio limit to 44. Set Performance Core 2 and Core 3 specific ratio limit to 46. Leave the specific Performance Core submenu. Set Efficient Core Ratio to sync all cores. Set Efficient All Core Ratio limit to 34. Set Max CPU Cache Ratio to 36. Set Max CPU Graphics Ratio to 40. Set BCLK Aware Adaptive Voltage to Enabled. Set CPU Graphics Voltage to Offset Mode. Set Offset Mode Sign to Plus. Set CPU Graphics Voltage Offset to 0.315. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. Thanks to the increase in base clock frequency, the integrated graphics now runs at 2.5 GHz. That provides a significant performance increase over our previous overclocking strategy. We see a performance increase of up to 51.27% in Firmark 1080p. The most exciting performance increase we see in Handbrake. The rise in unsliced frequency from 1400 MHz to 1750 MHz results in a substantial improvement of the QuickSync performance measured by Handbrake. When running Firmark GPU stress test, the average GPU slice clock is 2500 MHz and the average GPU unsliced clock is 1750 MHz with 1.4 volts. The average memory clock is 3875 MHz. The average GPU temperature is 61 degrees Celsius. The average GPU power is 26.177 watts. Alright, let's wrap this up. In my very first Raptor Lake overclocking video, I laid out my plan for Raptor Lake overclocking guides. I said I would have a look at each of the K-SKU variants, I would have a look at cryocooling, and I would maybe have a look at overclocking the integrated graphics. Now, as I said in the beginning of the video, I wasn't really planning on following through on that integrated graphics overclocking. However, after a brief check, I found out that overclocking the integrated graphics on Raptor Lake is actually kind of cool. Even though the IP and the overclocking process is identical to Alder Lake, the integrated graphics in Raptor Lake can be overclocked substantially further, right? It's the first time that I've seen a 2.5 gigahertz integrated graphics on an Intel desktop processor. Anyway, with this video, I'm wrapping up my Raptor Lake content. I've overclocked every K variant, the 13900KS, the 13900K, the 13700K, and the 13600K. I covered cryo cooling, and I've covered integrated graphics. Now it's time to move on to other platforms. I hope you've enjoyed my Raptor Lake content. So that's it for this video. I thank you for watching, and I thank the patrons for the support. As per usual, I will put up a written version of this video up on my blog if you want to read through the BIOS settings or check my specific benchmark results. If you have any questions or comments, feel free to drop them in the comment section below, and see you next time.